complex numbers, basically what we're talking about here is that the square root of -1 equals I, right? I is this little concept or idea that allows us to then calculate negative square roots. Like, for example, if you have the square root of like negative 32, you can change that into I times the square root of 32, right? Which you would then be all like, oh, that's like I times 4 roots of 2. So I think you actually want to write that like 4I square root 2. Because 32 is 16 times 2, right? And the square root of 16 is 4. So you'd get 4 roots of 2 by simplifying 32. Anyway, I'm really taking this and saying that could be the square root of -1 times the square root of 32. That's how you then say, oh, now that's I roots of 32. Okay? So that's a basic explanation of what I means, how it's represented. We're kind of reviewing properties of square roots also, how to simplify square roots. So it's, all of that action is going on here. Standard form of a complex. So this is just, I is just the way that we represent a imaginary number, okay? So flowing from this is the concept that if you square both sides of this, -1 equals I squared. So we also like to use that to simplify things. If you ever see an I squared, we kind of plug in -1 for it. We like to do that. So now you have the standard form of a complex number. Of a complex number. I'm sure you've seen this before as well, is A plus BI, where A and B are real numbers. A and B are real numbers. So there's this little side note here, which is kind of interesting and useful to use. A plus BI is equal to C plus DI if and only if A equals C and B equals D. So you can kind of equate these things that way. So a complex number is then, in that case, what we say here is the sum of an imaginary number and a real number. So it is the sum of a real number and an imaginary number. So obviously, like I said, A and B are both real numbers. So really, like BI is a product of a real number times an imaginary number, but then you're adding it to A, which is a real number. So we're going to talk about how to do a little bit of simplification here. Adding and subtracting them is actually probably the easiest thing. You have really all basic rules, and I think people know this, all basic rules of algebra apply here. So we're going to just do a couple of examples and show you how to work with these. Again, I think this is somewhat fresh in people's minds, but if not, it's okay. We're going to just hopefully take another 10, 15 minutes to cover it, and then I'll let you go. So first thing, if you have maybe 1 plus I plus 3 minus 7I. Essentially, you have to, when you're adding and subtracting, you're just combining like terms. And I say like terms, in parentheses. The like terms are the things that have the same sort of a concept going on. So when I do this, this is really just going to be like 1 plus 3 plus I minus 7I. You get what I'm saying? You smelling what I'm stepping in? Picking up what I'm putting down? Which even further, I can even say like, so obviously 1 plus 3 is 4. This is all also described as being like I parentheses 1 minus 7. You're adding the coefficients, and the i's are like a variable that's staying there with the coefficients. So this final answer would end up being 4 minus 6i. And so that's how you do your addition and subtraction of these things. Cool. So you just got to kind of keep track of whether or not you're adding or subtracting. So for example, and there's another one, if I have 4 plus 3i minus, 2 minus 6i, okay? And I'm doing this out. Sure, 4 minus 2 is 2. But now you got to kind of keep your negative straight. You got to go 3i minus negative 6i is really like 3i plus 6i. So that's like plus 9i, you see. So when you're subtracting, just pay attention. Careful. That's all. That's all that is. Okay. And so the same sort of concept applies when you're multiplying these as well. So that's adding and subtracting. Hopefully that makes sense. Any questions about adding and subtracting? And all your homework is going to be for the weekend is just to do a little bit of arithmetic with these complex numbers. They are useful because when we want to find all the zeros of a polynomial, we can find imaginary zeros and write them as complex numbers. So this is kind of like an addendum to the chapter learning about complex numbers. So multiplying. Let's do 3 plus 2i times 3 minus 2i. Ooh. Starting right off with a difference in squares there, sort of thing. Yeah. Anyway, so basically what you have to do is, you're still essentially going to FOIL and try to simplify. Yeah, that's essentially what's happening. So you're going to FOIL and then simplify. So what I mean by FOIL, I mean 3 times 3 is 3 squared, which is 9. And then minus 3 times negative 2i is like negative 6i. Okay. And then I got 2i times 3, so that's going to be like plus 6i. And then I got negative 2i times 2i, which is like negative 2 times 2 is 4, but then you got I squared. Ooh, yes. So now you got to simplify. This is when you got to know what's going on with this. So to simplify this, I still got my 9. You might notice that 6 minus 6 is 0. So those i's are gone. See you later. Now, there was also one point in time when we talked about how I squared is actually equivalent to negative 1. So I actually want to rewrite this as like minus 4 times negative 1. You're seeing what I'm saying there. So really this turns into like 9 plus 4. And so the answer is 13. And so the product of those two complex numbers is actually just a real number. It's kind of funny how that works out like that. Right? So, and actually, this kind of leads me to my next point, I guess. This is multiplying by a conjugate. Oh, spelling conjugate. Conjugate. I think it's a J and then a G. Conjugate. Yeah. A conjugate is when you just change the sign in the middle. Okay, so conjugate is, for example, if I have A plus BI, the conjugate of that is going to be A minus BI. And it's useful because you notice how when I multiply by this conjugate, I end up with a real number. So it's going to simplify some things for me. It's going to eliminate the imaginary number from the denominator in some of these fractions that I might try to simplify in a little bit. So that's a skill that we want to be able to do, is to identify what the conjugate is. And it just means change the sign in the middle of the two terms. That's what the conjugate is. Ooh, excuse me. Yes. Mm-hmm. So anyway, I did want to do another like just multiplying question. So just have people try this one out, like 2 plus I times 3 minus 4I. Just see what you get. Try it on your piece of paper there. Boom. There it is. So still, when you're doing your multiplication out, you notice that there's an I that's going to end up turning into I squared, which is then that I squared term. You always want to then rewrite that as like -1. And I sort of skipped from taking -4I squared and just rewriting it as +4 when I simplified there. So if you're confused about what happened, that's what I did to get to that point there. Yeah. I squared is -1. Which is that's the key of how I'm simplifying all that sort of stuff. Word up. Yeah. So you should end up there with 10 minus 5 i's. Now a little bit on I. Okay. Powers of I. Okay, these are kind of important. So I to the first is obviously just equal to I. I squared, as we were saying, gives you -1. Okay. I to the third is like I squared times I, right? Which is, in that situation, -1 times I. Because again, I squared is -1. So this equals -I. So, and then we have a pattern forming here. We're forming a pattern. I to the fourth power is going to be like I squared times I squared. And I squared is -1. And -1 times -1 is +1. You'll see. And so now if I go I to the fifth, I really have like I to the fourth times I, right? And we just said I to the fourth is 1 times I means I to the fifth is really equivalent to I. And there's your pattern, you see? I started at I went to -1, to -I, to 1, back to I. Guess what I to the sixth would be? -1. I to the seventh is then going to be -I. So it goes in this four-part pattern. I, -1, -I, 1. Now I'm back to I, -1, -I. That was to the seventh. I to the eighth is going to be 1. Let's see. Patterns. Okay. So the concept with that is, right, if you have I to the n and you want to figure out what that's equivalent to, take n and divide it by 4. Okay. And that is going to, let me actually, I think that's the next theorem that it tells you what's going on with that action somewhere like that or whatever. Where is that at? Somewhere in there. No, okay. Anyway, you just need to take it and divide it by 4. So for example, and that's going to tell you like what it's, so yeah, it's equivalent to essentially I to the n divided by 4. So like, for example, if I have I to the 54th power and I want to figure out what that's equal to. Oh, I want to figure out what the remainder is. Sorry. So I am going to say, well, what's 54 divided by 4? And 54 divided by 4 leaves me with a remainder of 2, right? 54 divided by 4 is 13.5. So what's actually going on there is like so 0.5 is like 2 over 4, right? So it's like 13 and 2/4 is what the division ends up being. Because it's 2/4, okay, that means that this is equivalent to I squared. And so that means that it's -1. Kind of confusing, maybe a little bit. So you take n, let me just erase some of this stuff. Fix what we said here. Don't want that. Okay. Oh, okay. I'm gonna fill that in now. Oh, now I've gone too far. Oh, now it's catching up to what I've done. Okay, there we go. So take the number, the exponent, divide it by 4, then whatever the remainder is, once you divide the 4 out, I raised to that remainder is what it's equivalent to. Let's sample another one there. Let's say I want to do like I raised to the 73rd power. Okay. I'm going to take 73 and I'm going to divide it by 4. And I'm going to see like what kind of a remainder there is there. So 73 divided by 4 is 18 1/4. This is 18 1/4. So the remainder is 1. So this is equivalent to I to the first power, or just I. You see. Because the remainder is 1. It's 1/4. It was 18.25 when I divided it out. So that's how you can figure out what they're equivalent to for like the really super large numbers of I. So I already talked about conjugates. So conjugates are the way that you would simplify quotients, okay? If you're going to do the quotient of complex numbers. The basic rule is multiply by conjugate. Okay, so here's an example. 3 plus 4i divided by 1 plus 2i. Okay? And I want to solve that. So the conjugate is whatever the opposite sign of the denominator stuff is, essentially. So for this one, I want to multiply the top and the bottom. So I want to take 3 plus 4i over 1 plus 2i. And I want to multiply the top and bottom by 1 minus 2i. 1 minus 2i. You see, this is the conjugate of the denominator. I'm going to get rid of the fraction by multiplying the top and bottom by the conjugate of the denominator. And then we just do a little quick maths here. So that equals 1 times 1 is 1. And then you should start to start it. You kind of figure it out. Like this ends up being minus 2i and then plus 2i. So that's like, see you later. And then I would have minus 4i squared. 2 times negative 2 is negative 4. I times I is I squared. We know I squared is negative 1. So negative 4 times negative 1 is like plus 4. So on the bottom, I get 1 plus 4. That's why I do this, because now I'm going to have just a regular fraction with a denominator that's a real number. I wanted a denominator that's a real number. So on the top, we got to do a little bit of work there. 3 times 1 is 3. That's going to end up being minus 6i, and then that's going to be like plus 4i when I do 4i times 1. So negative 6 plus 4 is negative 2i's. And then I got 4i times negative 2i is like negative 8i squared. I squared is negative 1, so that's like plus 8. Yeah. 3 plus 8 is 11. JK, I knew it was 11, y'all. Just trying to keep you fresh. Over 1 plus 4 is 5. So this is not quite technically in standard complex number form yet, but this is pretty close to the answer. You would actually want to rewrite this as 11/5 minus 2i over 5. And then there you go. That is in standard complex number form. That one. I probably would mark it wrong by like a fraction of a point. Someone asked if you wrote this as an answer on a test, would I mark it wrong? If it's asking you, I would need to be specifically saying standard form of a complex number if I was going to be that much of a meanie head. But anyway, right, I'm multiplying by the conjugate. That's the whole thing. Multiply by the conjugate because it gives you that number that you want in the bottom there, okay? So the whole point of this is that we can then use these skills to find all the possible zeros of a function. That includes their non-real zeros. So essentially, the whole thing is, right, finding complex, that's us, roots. You're going to use this stuff to find the complex roots. Anyway, the homework is just doing all this arithmetic, so go give that a shot. We'll talk a little bit more about it on Monday and maybe talk about the complex roots Monday and Tuesday. Have a good weekend. Love y'all. See y'all later. Thank you.
Thank you very much. Where do you post all these recordings?
I'm not posting the Zoom recording necessarily. I like recorded my screen, and it's gonna be like